Good morning, everybody. Hope everybody's doing well. It's been a while since we've seen each other, so I hope you've had a good past week, since it has been a week since we've seen each other. Got some administrative business to kind of go through very quickly at the beginning, and then we'll get into the actual lecture. Get my Barry White morning voice is what you're getting right now. Let's see. A couple things I'm going to list out since we're still ahead of time right now. Just as a reminder for myself. There we go. All right. So we're right up around 7:20. So let's go ahead and talk about this stuff. There is a quiz throughout the day today. So it starts at 10 a.m. You can log in just like last week. Log in anytime between 10 a.m. and 9 p.m. That is. And you could take the quiz. It's a 25-minute quiz, and it's on section 6.3. There you go. And I have done what I said in the email or the message I sent out to everybody. I limited the number of randomizations, so they're nice randomizations, not terrible randomizations, which I found out is a cool little trick you can do. So that's good. That actually helps for the exam as well, because I can control how nice the numbers are, because this is not an arithmetic class. It's supposed to be more about calculus. So sorry about that, but or sorry about the previous quizzes, but now from this point forward, it'll be very nice. So as far as computation, on the quiz, there'll just be one. It's a one question quiz. I'm trying to do my quizzes as one question each time, mainly because one, you're not rushing through trying to get to the next question. And two, because I would like all the quizzes to be worth the same number of points, so that I can, in the long run, start dropping quizzes. But it's hard to drop quizzes when you have quizzes worth different amounts of points. So I want to get them all to be around or at 10 points each, basically. The second thing I need to mention is, remember, we do have an exam on Friday. And that covers sections 6.1 through 6.5, right? And also the material in 6.4 that was from section 8.3, which again was already in the lecture in 6.4 and is in the homework in 6.4. So you've been practicing that no matter what. So don't forget about that. The study guide is a great way to practice for the exams. And it's the exam will be set up just like I would set up a quiz, as far as what questions I select, and making sure that the randomizations are nice. So yeah, I have a couple people were asking that question. So anyhow, all right. So that's that. Remember, I have office hours after to answer any other questions about homework or the exam or anything like that. Where we left off as a big entryway topic into integration techniques, and we talked quite a bit about the integration by parts method, but we didn't really, we did like a few problems, but not a lot. And if you look at the homework, which I meant to change today, so let me go ahead and just do that really very quickly, and then I'll showcase what I was going to say. So let me go ahead and just fix something really quickly. And done. All right. So the homework for section 7.1, share screen, yes, and go over to my second screen. There we go. The homework for 7.1, I have just moved to be due a week from today. I had it due on Monday. There's a problem with that. The problem with having that homework due on Monday is that you likely should be, honestly, studying for your exam rather than trying to do the 7.1 homework. I want you all to ace the exam. So I would prefer that you spend your time studying for that exam and then start the homework. Unfortunately, if that's how you do it, though, and if I still had it due on Monday, then the only time you'd be able to ask me questions about the homework for 7.1 would be on Monday office hour, which is kind of tough. So I moved that homework just now to be due on Wednesday. That does not mean you should wait till Tuesday to start it, because if you look at that homework, it's actually, let me go into student view. If you look at that homework, it's actually quite a few questions. And the reason why is because I want you to be awesome with with all the integration techniques. So there are 28 questions on this. Now, obviously, most of them are very computationally driven, but still, there are some that are going to be somewhat challenging. And so just note that that you should do, since there's 28 and it's due in a week, do like 4 a day. There you go. 4 or 5 a day, and you'll be okay. All right. So going back to our main lecture, and also allowing me to see the chat log. That's good. All right. So going back to what we were doing last time, we had talked about integration by parts. So given two differentiable functions, f and g, we know that the integral of the way that it's written officially is this: the integral of a function times what ends up being the derivative of another function, dx. Well, that integral can be found by finding what f is, which is actually just right here, so there's no big secret there, and the antiderivative of this other factor within the integral, that would be g, and then subtracting off the integral of f prime g dx. Now, I got to be honest with you, saying it out loud is actually more confusing than just doing it. And so the way that most of us within mathematics deal with integration by parts is the second way. The integral of u dv is equivalent to uv minus the integral v du. Much, much cleaner. It looks simpler. And as we go through and do problems, you'll see there is a nice, beautiful pattern that starts up. Now, some people have been taught a trick. There is a trick, actually, to doing some of these methods. I do not teach tricks until we have plenty of experience with integration by parts, and then I start releasing tricks. So let's go ahead and remind ourselves of a couple more things. One, my first piece of advice: integration by parts is almost entirely heuristic, based on experience or educated guess, rather than a hard and fast rule. It's often the best choice when the integrand is a product of two functions. However, that is not always going to be the case. There are times when you will use integration by parts when you only have one function in your integrand. In fact, it's very common to use integration by parts in that situation. But just letting you know, if you have the product of two completely different functions, like let's say x squared plus 1 times the sine of x, that is a massive clue that you're going to be using integration by parts. If you have a product of two functions, one of which you can integrate and the other that you can differentiate, well, then you are likely to use integration by parts. It's not the only way, but it is a good way. And then my last piece of advice here, before we go back into integrating using integration by parts, is the mnemonic Lie8 here. I normally do not teach this, but it is kind of nice to say it out loud a couple times, that when you're having a hard time trying to decide what you should choose as u, the piece that you differentiate. Remember, when you use integration by parts, you choose something to be u. You build a little table is really what you do. And you choose something else to be dv. You will differentiate u to arrive at du, and you will integrate dv to arrive at v. And this will allow you then to use integration by parts, because integration by parts tells you if you started with the integral of u dv, well, then that is u times v, which is these two right here, minus the integral of v, which is this guy right here, times du, which is whatever that ends up being right there. So it's a really kind of a nice, clean way to kind of pull everything together, and we'll see this in action throughout. But sometimes you're kind of stuck on what should play the role of u and what should play the role of dv. If you're ever really truthfully stuck, like just can't go anywhere, then following this mnemonic Lie8 is kind of helpful, because it tells you what you would choose to differentiate. That's what Lie8 is associated with. Now, my advice, really, my strong advice, which I don't have typewritten here, my strong advice is always to look for the biggest piece that you can integrate. Look for something to play the role of dv. It's a really, really good piece of advice, because you'll find that with that piece of advice, you can speed up your computations. All right, so let's go ahead and go into it. We already did this example last time, so I'm not going to bother with this, but let's move on to the second. Nope, let's go on to the third example. There we go. So here we have an integral, and it's actually a definite integral. So this will not have the plus c at the end. You're actually going to completely evaluate this integral and get a constant at the end. So here we have a wonderful set of choices. Now, I'm going to start what you should be doing from this point forward, listing out possibilities. For example, so I'm going to write it this way: possible techniques. And I don't expect you on an exam to do this list of possible techniques. I'm writing it for your benefit so that you know that I'm actually considering different integration techniques prior to diving into integrating. So for example, one possible integration technique here, one integration technique that I might want to employ would maybe be a U substitution. That seems like it might be a good idea. So U sub. Now we only know two, honestly, integration techniques. So right now it's a dead end lane, right? We either have U substitution or we have integration by parts. But by the end of this chapter, we'll have about 8 different integration techniques. And so it's very important that you get used to making choices as we move forward. So let's take a look at this. U sub might work, and then integration by parts is almost a no-brainer on this. Notice it's a product of one function with another function. Well, maybe I shouldn't rope up the dt there. I'll rope up these two. So it's a product of 2 different functions, one of which I can integrate. The other one, I don't know how to integrate. Let's just pretend I don't know how to integrate the natural log right now. So this is the one I would differentiate. So to me, integration by parts is also a really good choice. And most of us just call that by parts. Now let's try either of these methods. So somebody might say, well, I'm going to do a U substitution, and I wouldn't blame you. I'd probably say a U substitution might be a great idea. So I will use a different color for U substitution. I'm choosing red, not because it's a bad idea, just because I'm using a different color. That's all. So try number 1. We're going to use U substitution. Again, when you're going through and doing integration, you're going to find this when you go through those 28 problems on the 7.1 homework. You're going to find that you're going to make wrong turns a lot, and it's okay. It's totally fine to make a wrong choice. You learn from making wrong choices, actually, especially with integration. It's probably one of the best ways to learn is to make a mistake. So let's go ahead and try U sub. I'm not saying that's a mistake. I'm just going to try it. The obvious U substitution here would be U is equal to the natural log of t. If U were the natural log of t, then du would steal away a 1 over t dt. Well, notice I don't have a 1 over t dt to steal, but that doesn't matter, actually. I could still say that implies, multiplying both sides by t, that t times du will replace a dt. If you do that substitution, something frustrating happens. Our integral, which was going from t equals 1 to t equals e, is now 2 times, well, I had a t to the 4th. However, dt I'm going to replace with a du times a t. So that 2t to the 4th is now a 2t to the 5th. I'm going to power that up by 1. And the natural log of t, well, I get to replace that with a u. And you could see, whoops, hold on. Maybe I should do it this way. 2t to the 4th, natural log of t, dt becomes, that's what I'll do, an integral. I'm going to at least write my limits in terms of u. This again was 2t to the 5th, and then we had, let's see, du, right? Oh, u du, sorry. There we go. So this is where we end after we do our u substitution. And you could, I suppose, if you wanted to, say, well, if t is equal to 1, that will imply, just plugging that into our natural log there, that implies that u is equal to 0. And if t is equal to e, that will imply u is equal to 1, which is actually a nice looking set of limits. But again, we're here. And notice that integral is a mixture of two different variables. Not only did we move from two different functions, which was already hard enough, now we're to two different variables mixed in here. And you can move completely into the world of u if you want to. That's totally fine. But I'm just letting you know, you'll still have to do integration by parts here. So if I grab that little relation between u and t, I could easily see that wherever I have a t, I can exchange it for e to the u. That's what t is equal to based upon what we allowed u to be. And so you end up having this equivalent integral from u equals 0 to u equals 1 of 2 t to the 5th, which is e to the 5u, times u du. And again, you have this mixture of functions. So here's a good example of sometimes taking what looks to be the more elementary or easier route still leads to the harder route. This still leads to integration by parts. We still have a product of two functions. Now, I am okay with going ahead and continuing this as if we just committed ourselves to this direction. I'm totally okay, and I think that I will continue this. But when we're done, I'm going to go back to the very beginning and say, well, what if we had done u substitution, or sorry, by parts right from the get-go? But let's go ahead and just finish this out to see how this specifically is done using by parts integration. Now, something I want to mention is before you do a by parts integration, pull out all constants. It's just much easier to deal with. U e to the 5u du. Also, note that you can change the letters of your integral all day long. So notice that all of the variables within this integral are the same. It's u going from 0 to u going to 1, u e to the 5u du. U is just a placeholder for a picture. You can call that whatever letter you want right now because they're all the same variables. So because I don't want to confuse myself, I'm going to switch everything to x's. Nothing wrong with that. It's just a letter. Nobody cares. I just think that it's a little bit easier because I'm going to do a by parts integration. And when I do by parts, I use the letter u in my by parts integration. So I would prefer to not have u already used up. So let's build our table for by parts. When you build your table, I notice that some students do it completely different than how I do it, and that's perfectly fine. You could do it however you want if you've learned this before, but I do it this way. Just build a nice little grid, u versus dv. I could see, by the way, why some students, maybe I do. No, I'll screw it up if actually, I think I will do it this way for a very specific reason. So we're going to choose u and dv. U is the piece that we're going to differentiate. dv is the piece we're going to integrate. And remember what I said earlier, choose dv if you can to be the largest piece you can integrate. If you can integrate both of them, well then, choose u to be the piece that will disappear when you differentiate. And if you look at those two pieces, the piece that will disappear or change forms when you differentiate will be x. So I'm going to let u equal x because, again, when I take its derivative, x changes form to a constant. Just derivative of x times dx. dv, on the other hand, that's going to be what I integrate. So we have e to the 5x dx. We're going to integrate that. Notice, by the way, each piece of our integrand is represented. X is represented right here. And just getting the highlighter working. E to the 5x dx is highlighted in blue right there. So we have all of our integrand represented. If you integrate e to the 5x dx, you'll get v is equal to e to the 5x, because that technically sort of the antiderivative of e to the 5x. However, that x is being multiplied by 5, so we have to do the opposite of multiplying by 5 to offset that. That's that trick I taught you from day one in this course, how to integrate very quickly. All right. So I have everything set up. I know the integral of u dv is supposed to be u v minus the integral v du. Now, I do want to mention here that we are not dealing with the integral of u dv. We're dealing with the integral of twice u dv. So I'm going to go ahead and just make my little mention off to the side here that we actually have twice some integral. So it's going to be twice all of this stuff. It's just a little bit easier. That I keep that constant off the side so I don't have to deal with it over and over again. All right, let's go ahead and finish by parts. It's actually pretty fast once you get used to it. It's 2 times u times v. Well, that's 1/5 x e to the 5x minus the integral v du. V right here and du right there. So minus 1/5, I can factor that out at least, e to the 5x, and then dx. Now remember also, these are definite integrals. That's actually what we were dealing with. Our integral went from x equals 0 to x equals 1. So I'm going to go ahead and place little pipes on these. It's from 0 to 1, and our integral here is also going to go from 0 to 1 because it was a definite integral. Now let's go ahead and evaluate. Twice, plugging in 1 into all this stuff, we get 1/5 e to the 5th. If you plug in 0, it's just gone, so that's nice. Minus 1/5 times the antiderivative of e to the 5x, which is going to be another 1/5 e to the 5x from 0 to 1. And now we just finish this out. Twice the product of, or the summation, 1/5 e to the 5 minus 1/25. And then if you think about plugging in 1 into that, we get e to the 5th minus, and then you plug in 0 into that, e to the 0th, which is 1, but I'll just write it as e to the 0th first. And then you just clean things up. And cleaning things up just means distribute that 2 through if you want to. You don't actually have to, but you could. Or you could factor out constants. For example, I could factor out 1/5 because each of those terms has a 1/5 in common in the parentheses. So that's what I'll do. I'll factor out a 1/5. And I'm left with e to the 5th minus 1/5 e to the 5th, which I could clean that up as well, plus 1/5. Because again, remember, I factored off a 1/5 off of this, so that's just it. So in the end, my final answer is 2/5 times 4/5 e to the 5th plus 1/5. Oh, yeah. And actually, I could still factor out a 5th, can't I? So let's go ahead and do that. 2/25 times 4 e to the 5th plus 1. Let me just double check. 4/5. Yep, that's it. So that is, had we done u substitution first, that's what the answer would be. Nothing wrong with that. Notice there's no plus e because it's a definite integral. So you just get a nice, beautiful constant in the end. Something that is very common to forget, I often do, is that we have just found the area underneath this curve from 1 to e. Sorry, just having a drink of chai there. But yeah, that's just something to note, that that's the whole point of integration, definite integration, is to find the area underneath the curve. So we actually found that. Very complicated integral, it seems. It's actually, in the long run, not too terrible. But now let's go ahead and do try number 2. I'm going to rope up that try number 1. I'm going to move it over to the right or left here. There we go. Wish you could do that on a whiteboard. And then I will break this and I'll go ahead and do try number 2. Try number 2, by the way, there's no need for you to do 2 tries if you already get to an answer. There's no need for you to do 2 tries, but I'm just going to do a second try here. It's just to showcase how you would do this had you done by parts from the get-go. So by parts from the get-go, you see your integral and you go, okay, of these 2 pieces, which is the one I can integrate? What's the largest piece I can integrate? Well, I'll go ahead and highlight the largest integratable piece. I can integrate this stuff and this. That's the largest stuff I can integrate. The only thing that I can differentiate really is the natural log. So that's how I'm going to make my choice on what u and dv are. So let's go ahead and make our table. There's u. I'll get in the habit of writing u and dv right next to each other. So our choice to integrate is going to be 2t to the 4th dt. And our choice of what to differentiate will be the natural log of t, because we don't know the integral of natural log of t yet. All right, so let's go ahead and differentiate this natural log. That's du is equal to 1 over t dt. And let's go ahead and integrate this dv, of which is equal to 2t to the 4th dt. Integrating, we would add 1 to the power, divide by the new power. There you go. And now we just go ahead and use the by parts algorithm. In this case, I didn't factor out the 2. Notice I didn't do that. I wasn't even thinking. I just didn't do it. That's totally okay. So we have this integral from 1 to e of 2t to the 4th natural log of t dt is equal to u times v, so that's 2/5 t to the 5th times the natural log of t, and that's going to be evaluated from t equals 1 to t equals e, minus the integral, let's see, u dv, v du, right? So v du minus the integral of that stuff right there. I'll pull the 2/5 out of the integral there, 2/5, and we have t to the 4th dt, and again, that's evaluated from 1 to e. Notice our simple method that we did first, which was u substitution, it required quite a bit of work. I mean, you can see all that red ink. But here, we're actually just immediately evaluating. If you go ahead and plug this in, you get 2/5 e to the 5th natural log of e, which we know is 1, minus 2/5 1 to the 5th natural log of 1, which we know is 0, minus 2/5 times the antiderivative of t to the 4th, which is another 1/5, t to the 5th evaluated from 1 to e. Cleaning this up, and you can't avoid, by the way, a lot of arithmetic cleanup when you work with integrals. It's just life. That's how that works. But the arithmetic cleanup here, we have, what is this, 2 over 25, and then we have e to the 5th minus e, minus 1, actually, sorry. And combining things up, both of these have a 2/5 hanging out, so I'll just factor out a 2/5, and we're left with e to the 5th minus 1 over 5 e to the 5th plus 1 over 5, and then that e to the 5th minus 1/5 e to the 5th is 4/5 e to the 5th, and we can factor out a 5th. So it's 2/25 times 4 e to the 5th plus 1. Notice in the end, the answers are identical. They should be. And notice less ink. on the immediate by parts method. You had to do by parts in both cases too. So don't always knee jerk to the easy method. Give yourself a chance to do a harder method, and you might be pleasantly surprised. So questions on this first, or I guess in this case, the third example in line, while I take a swig of chai. Okay. Well, you can always type in chat if you do have questions, but I'm going to hop forward. I chose some of the problems from your homework, honestly. This is one of them, because I just loved this question. I've never seen a question like this before. Such a cool question, and very attractive to go down the wrong paths here. First of all, just listing out the possibilities, and I'm just going to call those possibilities. Possibilities. Or tactics. I should call them tactics, honestly. So one thing you might think U sub would work here. If you think a U sub would work, have a little forethought as to what will be the ramifications of your U substitution. If you let U equal the argument for the natural log here, then du needs to steal away a 2x plus 16 because that's a derivative of that. And you don't have a 2x plus 16 to steal away. So my du is not a really great du. So I am going to immediately say U substitution is a terrible idea. Really, really bad idea. So let's go ahead and just list out the only other possible technique. Let me go ahead and just say technique or tactic. Is by parts. By parts is the only other possible tactic that we know of right now. However, there's actually a different one we will be using. If you try to use by parts here, it is a bit of a mess, because if you just knee jerk into by parts, so I'm going to write this as try number 1, which I'm going to just say, let's call this a without thought by parts. That means that you're not really thinking about what you're doing. You're just kind of running like a bull through a China shop, just running through trying to get to the other side. And that is probably a bad idea. But to be honest with you, I have always been guilty of this. Of just immediately running in and trying to get to a solution when in reality you won't be able to, or it becomes incredibly difficult. So if you try to use by parts immediately, think of the biggest thing you can integrate here. Now, really, all you have is natural log of something, dx, and you can't integrate the natural log. So you have nothing you can integrate other than dx. The thing you can differentiate is the natural log of x squared plus 16x plus 63. And there's nothing wrong with that, actually. There's nothing wrong with having the integration piece be just dx. That's okay. V will be x, fine. And when I take the derivative of u, I get du, and I'll need more space because this is going to be a chain rule. I get that du is equal to 1 over the argument of that natural log, x squared plus 16x plus 63, times, again, by the chain rule, the derivative of that argument. So times 2x plus 16. Now, that's not very attractive because you're going to have to integrate that in a second. So let's just see what I mean by that. So the integral of our u dv is going to be uv minus the integral of v du. Well, u times v here, that's just going to be x natural log of x squared plus 16x plus 63 minus the integral of v times du. Let's go ahead and take a look at that integral. V is x, du is that fraction, that rational function. So it's going to be 2x squared plus 16x all over an x squared plus 16x plus 63 dx. Good luck. That integral on the back end, I'm not going to say it's impossible. It's not true. It's pretty possible. I suppose you could do it. It'll take a lot of massaging of the integral. In fact, quite a bit. I could show you tricks on how to do it, and it actually is very, very possible. But let me see. I would add 63 to the numerator. Okay, and I'd split that apart. I get 1. Yeah, so if I start showing you right now, it's going to go down a rabbit hole. I don't want to get into the rabbit hole right now. So when you get into a point like this, it's good to hit pause. Don't erase your work. Just pause on this method and go back to the actual original integral and ask yourself, could you have done something else? And this is a mantra that I give to my calculus students, my Calc 1 students. And in fact, I say this pretty much through the entire math curriculum as I teach through the tree, is that you should always perform arithmetic before algebra, algebra before trig, trig before pre-cal, and pre-cal before calculus. Calculus is the very last thing you should be doing in calculus. So if you had the choice of doing some algebra first, you could, by just realizing, one, that this is a factorable trinomial there. Now you may think, well, that's not going to help me, is it? But it will actually help you. You'll have the integral of the natural log of, 9 and 7, x plus 9, x plus 7. And you might say, how does that help? By the way, I do want to mention, notice all of my integrals have this dx, so should yours, right? Don't just write an integral without that differential on the back end. That'd be wrong. So I just see that happen in Calc 2 every once in a while. So that's my warning. But this will help me because I have a property of logarithms, again from algebra, that says I can break apart this logarithm into the natural log of x plus 9 plus the natural log of x plus 7. And while I have broken it into now 2 integrals, because I will actually write this as 2 separate integrals, you may think you've doubled up your work, but actually you've made your work easier. You're working with simpler statements. You'll still have to perform by parts integration on each of those separately, but it's a much easier by parts integration. So notice that's me using algebra before I step into calculus. Be highly aware of that. So now I'm going to go ahead and do my by parts integration off to the side, actually. So in the first one, maybe I'll color code this for us. This first one that I'm writing in blue, natural log of x plus 9 dx. Okay. We choose something to differentiate and something to integrate. Well, obviously you can't integrate the natural log of x plus 9, so we're going to differentiate that. And so the piece we're going to integrate is the dx. Notice my entire integrand for that first integral is represented. Du in this case is going to be 1 over x plus 9 dx. And v, which is the antiderivative of dx, is going to be x. Now, the trick I was going to mention here down this rabbit hole, we'll still have to use, but it's in an easier form, so much easier to teach it. All right, so that blue integral is going to turn into the following. Maybe I should do black equal sign and then blue for the rest of it. Equals u times v, which is x natural log of x plus 9, minus the integral of v du, x over x plus 9 dx. We still have a second integral to go through, but that is at least the by parts method applied to the first integral. Now, the second integral, I'm going to do that in green. We have this green natural log of x plus 7, and you can pretty much see just by the pattern we developed, you can kind of steal the same idea. I'm just going to go ahead and write it because I think that you all are advanced enough right now to know if you see a pattern, you just follow the pattern. So this is going to be plus x natural log of x plus 7. The only difference between these two integrals is the plus 7, minus the integral x over x plus 7. Basically the same exact integrals otherwise. All right, so I really only had to do by parts once to get to this point. So let's kind of clean this up. It's not actually going to be cleaned up too much. In fact, I'm not even going to bother rewriting it. I'm going to talk about what we do now. So people will stare at like, for example, this integral. People will stare at that and say, I don't know the antiderivative offhand, and I don't even know how I would begin. People will do u substitutions. Actually, a u sub would be perfect here. U sub would be fine. You could totally let u be the denominator. If you let u be the denominator, then du would just be dx. And I should write it rather than say it so that you can see what I'm talking about. So if you wanted to, totally fine. You could say, I'm going to let, u is already being used, so I'm going to let w equal the denominator. If you do that, then dw is dx. And you would see that this entire integral would turn into the integral of something over w dw. That something is an x upstairs. And everybody stops and says, oh man, I can't have a mixture of variables. Well, you don't really, because you have this relationship between w and x right there. So if you have an x by itself, you could say, well, that x by itself is the same thing as w minus 9. And believe it or not, this integral is much easier to deal with than the original, because you can break that fraction up. That fraction is just 1 minus 9 over w dw. You know how to integrate 1, and you know how to integrate 1 over w. So that is a very fair technique to use. So I'm going to go ahead and say that our integral, this piece right here, is still x natural log of x plus 9 minus, and I'll put a little bracket here. Be very careful. We spend years telling students to put parentheses after a subtraction sign because you'll need that quite a bit in this course. So we know that integral of x over x plus 9 dx will turn into the integral of 1 minus 9 over w dw. Now, I still have all this stuff hanging off back, so let me just rewrite that because I want to showcase another method that you could have used. So natural log of x plus 7 minus the integral of x over x plus 7 dx. All right. Let's go ahead and deal with this integral here. X natural log of x plus 9. It's just sitting there the entire time. Minus, we have an integral of 1. Well, the integral of 1 is just w. And then we have minus a negative, so plus 9 integral of 1 over w dw. Now, I wanted to write that because some people will get lost if I immediately integrate. So I'm just doing it that way just to showcase my mindset. I'll still write this one off back because I just want to showcase, again, a separate method you could have done from the get-go. The antiderivative of 1 over w, natural log, absolute value of w. That absolute value throws people off all the time. So minus w plus 9 natural log absolute value of w. And then we have the rest of this stuff, right? Plus x natural log x plus 7. And then minus this integral off the back end. Now, here's where I really want to talk about that integral off the back end. Could we have done, because that integral off the back end is basically the same as this integral of x over x plus 9. We could have done both of them at the same time just to save time. However, I want to showcase a different way you could have done that x over x plus 9. So I'll do this in a different color so it really stands out to you. Well, we did have an x over x plus 7. But you know what? I'd love it if it were an x plus 7 over an x plus 7. That would be awesome. Well, then I'm going to make it so. However, that's kind of adding something that wasn't originally there. So you're going to have to offset it. A very, very common trick in calculus is to add and subtract a number. And you do that add and subtract of the same number to get to a form that works for you. So let's go ahead and say this is x natural log of x plus 9. I'm just rewriting all this stuff. Minus w. Well, w is x plus 9. So I'll go ahead and write that in here. Minus the quantity x plus 9. Plus 9 natural log absolute value of w, which is x plus 9. Something will be said about that in a moment. Plus x natural log of x plus 7. And now I'm going to split this integral into two integrals. It's the integral of x plus 7 over x plus 7 minus 7 over x plus 7 dx. And you can see why I did that, because x plus 7 over x plus 7 is just 1. Integrating 1, super fast. Let's go ahead and clean this up. This is x natural log of x plus 9 minus x minus 9 plus 9. Since we already, from the get-go, we're dealing with a natural log of x plus 9 without absolute values, that tells us that x has to be, or x plus 9, sorry, has to be positive. That was implied in the original problem. Way back up top, this product here is the same thing as x plus 7 times x plus 9. When we split that apart, that showed us, sort of, that x plus 9 had to be positive. Now, I say sort of because there is actually a caveat with that statement. I don't want to go down that rabbit hole. That's really meant for very theoretical conversations. But the reality is x plus 9 we'll just assume is positive, even though technically it might be negative by accident. Plus x natural log of x plus 7 minus the integral of 1 dx plus 7 times the integral of 1 over x plus 7 dx. Now, I did all of that work in red to again showcase a long-winded method that you could have done very quickly. Because as you're seeing with how we're integrating x over x plus 7, if you can do this where you add something to the top and then subtract it so that you get a fraction that'll become the number 1 and a second fraction that's easy to integrate, then you can avoid all that other stuff we had done earlier, and you get down to a beautiful x natural log of x plus 9 minus x minus 9 plus 9 natural log of x plus 9 plus x natural log of x plus 7 minus the antiderivative 1 is x plus 7, the antiderivative of 1 over x plus 7 is the natural log of, normally I would say the absolute value of x plus 7, but we actually have a natural log of x plus 7 without absolute values, which tells us that x plus 7 is positive. So I don't need the absolute values just by virtue of that. And that last integral will pop out a constant of integration as well. Believe it or not, that is an easy integration by parts problem. You may look at that answer and go, what just happened? How in the world am I supposed to do that? You will be able to. Trust me. It is actually incredibly swift to do something like this, but you just have to get used to it. Some things I want to mention here. One, if you're a fan of looking at answer keys, you will never match, or you'll rarely get an answer that matches an answer key. So all of the coding that's done for online homework systems when it comes to integration, they allow for differences by constants, because this plus 9, or sorry, this minus 9 is actually usually just bled into that C. That C is just some arbitrary constant. So 9 will bleed right into that. And so really most people will write this answer as x natural log of x plus 9 minus x plus 9 natural log of x plus 9 plus x natural log of x plus 7. Oh, actually, I don't need that. I can write this minus x as a minus 2x, can't I? Because I have a extra x right there. And then plus 7 natural log of x plus 7, and then plus c, where c is now a new c, which is the combination of -9 and an old c, basically. That is the answer. Yes, there are other ways you could write it, because you have properties of logarithms where you can combine these, but one is the same as the other. I don't really care. It's not that big of a deal, but you could technically combine these up if you want to. If you did so, yeah, you would get what, x plus 9 natural log of x, and x plus 7 natural log of 7. Well, that's actually the best you can hope for with that. So, yeah. So there you go. This is the answer. Pretty impressive group of work there, actually. Yeah. That deserves questions if people have questions. That's a pretty beefy. Is it incorrect to leave the -9 as part of the answer? That's a great question. No, it's totally not incorrect, because and it won't mark you. It shouldn't. A well-designed, well-written, coded question will accept any constant, not multiple. What am I thinking of? Any constant, any answer that's off by a constant, maybe I should say, is what it will accept. Why was it -9 but no -7? Why was there a -9 but no -7? Oh, it's because, okay, that's a great question. Avi is asking, though privately, so nobody can see it, but Avi's asking, hey, if they're the same integral, like if these two integrals right here, let me zoom in. If these two bad boys right here are exactly the same, but the first one gave us a -9, why didn't the second one give us a -7? Sorry, just having a drink of chai. And the reason why is the way I integrated. In the very first case, I decided, well, let me do a u substitution to make that an easier integral. And then I got down to here, and then I got to this, and I integrated, and that was fine, right? And then when I resubstituted, I get the x plus 9. That's where the 9 came from. However, in the second case, I didn't do a u substitution. Instead, I used a very ingenious or creative trick of, let me make the numerator the same as the denominator. Well, sort of. And then I broke those two fractions up, and now I'm integrating 1 and 1 over x plus 7. And I know the integral of 1 over x plus 7 is just a natural log absolute value of x plus 7. In that case, with the avoidance of the u substitution, I avoided that extra constant of integration. That 9 is from that constant of, or I'm sorry, from the u substitution that we did. So that's why there's a difference in these quote unquote answers, even though the answers are exactly the same. Yeah. They're just off by a constant, perfectly fine. Really, really very I love this problem. It's a really cool problem. But again, it's a problem I hadn't seen before. And so when I chose it for the homework, I thought I had better talk about this because I have a feeling people are going to run in circles on this. So there you have that. You'll have something like that on the homework. Let's go ahead and move into integration by parts, tricky trig. And we've already done one last time, so I'm not going to have to rehash that because it's the same use substitution by parts process. Let's go ahead and try a quote unquote second example. In this second example, I'm glad I have it on here because I had looked through the homework as I try to do prior to the lecture, and I saw a problem like this and I thought, oh man, I hope I have that in the lecture because people are not going to know how to do this. So let's talk about this, a seemingly innocent integral. Now, for the moment, let's just pretend that was not the sine of 2, or I'm sorry, x times the sine squared of 6x. Let's just pretend it was x times the sine of 6x, which was very similar to this one. In fact, it is exactly that one, right? So in the previous or last week's lecture, when we did this problem, it wasn't too terrible. We chose u to equal x, the piece that we, whoops, I'm trying to highlight, but I'm circling with a white pen. The thing we chose to differentiate was x. The thing we chose to integrate was sine of x. And then we got down to uv minus integral v du. And then we worked that thing out. It became 1. That was the area underneath that curve. So we already have an example of what if the power on sine was 1. But now we're dealing with what if the power on sine wasn't 1, but instead 2. How will we take care of that situation? And this goes back to what I said earlier. Arithmetic before algebra, algebra before trig, trig before pre-cal, pre-cal before calculus. And technically, trig, pre-cal is just a blending of algebra and trig. So it really should just be arithmetic before algebra, algebra before trig, trig before calculus. So if you were to try to do by parts immediately, and let me just list out tactics here so that you get used to that idea. Tactics. So we only have 2 to go with, u sub or by parts. Right now, just looking at this, a u substitution is going to do you no good, other than if you were to say, I'm going to let u equal 6x. Great, good for you. If you did that, you'd still have the integral of 1/6 u sine squared of u du. Still, that's just as bad as the original. So I'm not going to do a u substitution. You may say, well, what if I let u equal sine squared? Well, then, if you let u equal that, sine squared, du would have to steal away a 2 sine of 6x cosine of 6x times 6 by the chain rule. And I don't have any of that to steal away. None of that. So that is going to also be a terrible idea. So a little bit of forethought, like just looking ahead, it will pay back immensely in the long run. You have to get used to being able to look at something and mentally just kind of doing the gymnastics of, will a u sub work? U sub is a bad idea. I'll write it down and cross it out just so that you know I considered it, but it's totally a terrible idea. And now we're going to do by parts. Now, as written, by parts is pretty terrible as well. If you try to use by parts on here and you say, okay, well, something's going to play the role of u and something's going to play the role of dv. Well, what's the largest piece you can integrate? And if you say sine squared, you're wrong. You don't know the integral of sine squared. You know the integral of sine, but not sine squared. So the only thing you can really integrate here is x dx. The thing you can differentiate is sine squared of 6x, which gets us back to that stupid du that we just found, du being 12 sine of 6x cosine of 6x, and v equaling 1/2 x squared, because that's the antiderivative of dv. And think about what this is going to look like if you were to say, okay, this integral is going to be uv minus the integral of v du. If you do that, well, uv is easy. It's 1/2 x squared sine squared of 6x. Yay! Minus the integral of v du. Well, that's going to be 1/2 of 12, so it's 6. And then you have an x squared sine of 6x cosine of 6x dx. Do you notice that integral is actually worse? So using by parts like this, you get to a worse integral. It went from a single sine squared times x dx to now not just a sine, but a cosine dx and x squared. You powered up x there. So that didn't get any better. So how the heck are you going to do this? Well, if you run into the situation, you're working on something and it just gets worse and worse and worse, that means there's probably something you should be doing prior to calculus. And in this case, we're going to, I'll just say stop. Stop. And I'll say trig before calc. Well, what trig can you do is probably what you're asking yourself. And this is why I'm a big stickler for all of my students as we go into pre-cal and calculus, stuff like that. I always tell them your trig had better be on point because you're going to be in the middle of a problem. Nobody's going to review trig for you. And you're going to just have to remember a half angle identity. And here we are. We're at that point. You have to remember that the sine of 6x is plus or minus the square root of 1 minus the cosine of 12x. You just have to remember that. That you should know from your trig prereq. Legitimately, like, no. That should be like, oh, yeah, totally. I remember that. But most people don't. I don't blame you. It's just, it's one of those things that I don't know if maybe all instructors try to get you guys to remember this, but you do have to remember this. If your trig is weak, watch my videos on it or just open up a trig book and review your trig. If you square this out, obviously it breaks the square root. It makes everything positive, and you're now dealing with the integral of x times 1 minus the cosine of 12x all over 2. Obviously, that 2 could be brought out front, but I'm just taking my time to showcase this. So I'll bring that 2 out in front of the integral. And you have the integral of x times the quantity, 1 minus the cosine of 12x. Now, do not convince yourself that you have to tackle the integral as written. Distribute. It's totally okay to do that. That's why you learned algebra, right? So I can distribute. So let's do that. 1/2 integral of x minus x cosine of 12x. And let me tell you, that is a much easier integral because I can integrate x. So the first part of that, I could totally integrate. The second part is definitely going to be a by parts. How do I know? Because of the previous problem we did. The previous problem was an x times a trig function, specifically the sine, but we're just changing it out for a cosine. Nothing big. So we're going to have basically the same problem as before, mixed inside of a problem we're currently doing. So let's make our lives a little bit easier. One, by moving my equal sign and moving everything over. So let me just go ahead and give myself some room. I have a habit to lean on the right edge of my page. So let me just move that over and erase this. Erase this. Let me say that again. There we go. All right. So this is going to equal 1/2 times the integral of x is x squared over 2. Yay. Minus the integral of x cosine of 12x dx. Now, my best students, honestly, are the ones who take their time with this process. So I'm going to take my time with this process as well. distributing the 1/2 through, I get x squared over 4 minus 1/2, and then integral x cosine of 12x dx. All right. Now we're ready to tackle that very final integral. And I will do that off to the side. We're just going to create that table, u versus dv. We're going to integrate a piece and differentiate a different piece. Now, technically, you can integrate either of those pieces. So if that's the case, switch to choosing what you're going to differentiate. You differentiate the piece that will change forms completely, and x changes to a constant. So that's what I'm going to differentiate. And we talked about it last class. What happens if you chose the trig function to differentiate? You would go in circles. You can watch that video if you want to, but that's what will happen. You'll just go in circles if you choose the cosine to differentiate. Let's go ahead and integrate that cosine of 12x dx. The antiderivative of the cosine is the sine, but it's the sine of 12x, so we'll have to offset that 12 with the division. And now we are ready. Remembering the algorithm is really what it is. We have, let's see, this x squared over 4 is just going to hang out for a while. Same thing with this minus 1/2. It's going to hang out. Let's see, u times v, that's going to be 1/12, sorry, x sine of 12x minus the integral of v du. So minus 1/12 integral of sine of 12x dx. It's like it leads to more and more integrals, but actually they get easier and easier as you do them. It should break into easier and easier integrals. All right, so let's finish this out by distributing and cleaning things up. So this is x squared over 4 minus 1/24 x sine of 12x. See, distributing this negative 1/2 across, it's plus 1/24. And then the antiderivative of sine of 12x is going to be a negative. So I'm going to change this to a minus sign. Actually, I'll do it this way. A negative 1/12 cosine of 12x. And then we tack on a plus c at the end because we finally finished our integration. Notice I don't put out a constant of integration until the very end. Because technically, each time you run an integral, it's popping out a constant of integration. So when I integrated this x here, there was a constant of integration that pops out, but I just reserve writing that until the very end. And I glue all those constants of integration together as just a single c. The final answer is going to be an x squared over 4 minus 1/24 x sine of 12x minus 1/288 cosine of 12x, and then plus some constant of integration c. And everybody knew, I know you guys knew it, that the antiderivative of the original x times sine squared of 6x dx, I knew you guys knew that that was just going to be x squared over 4 minus 1/24 x sine of 12x minus 1/288 cosine of 12x plus c, but I thought I'd go through all the work anyway. So you get the joke, I hope, that you would never know the antiderivative of x times the sine squared of 6x. That would be like, if you happen to know that offhand, you're a savant. This mechanical work is totally necessary to get these pieces. So yeah, that's a really cool review of kind of remembering the trig. Can we have used the power reduction formula instead of the half angle identity? Same exact thing, actually. I've never understood why the textbooks call it a power reduction formula when actually it is just a half angle identity. It's the same thing. So power reduction formula is this. If you have, I'll pick on the sine since that's the one we have. If you have the sine squared of x, that's the same thing as 1 minus the cosine of 2x over 2. But that is the half angle identity. It's just the square of it. Yeah, it's just To me, I always called it the half angle identity. Yeah. It's the same thing. It's the same thing. It's the square of the half angle. Yeah. Yeah. Yeah, you will have to know that, by the way. That becomes like a very important. Also, double angle identities, super duper important. In fact, you can see a double angle identity here. Multiply both sides by 2, subtract 1, and then multiply by a negative. You'll have what the cosine of the double angle is. So, yeah, double angle identities you'll have to use quite a bit. And some indifference of angles identities you'll have to use quite a bit too. So they're all over the place. Yeah, it's a good question. So other questions on this. Beautiful, beautiful example, because it really does kind of illustrate the level of thinking you need to be at. You need to really grab onto your old material. Everything you've learned in the past is now viable and usable today. Where do we get the square root from? The square root is actually just from the fact that normally, let me go back to this one. Normally, the sine of 6x, if it wasn't the square, the sine of 6x would be the plus or minus the square root. That's the half angle identity. But because we're dealing with the square of that, when you square both sides, well, there you go. So it's just from the half angle identity. Yeah. Other questions before we tackle yet another example. Then what's sine cubed? Yeah. Yeah, right. That is a question. Then what is sine cubed? There is no formula for sine cubed. Nope. It's sine squared times sine. As good as you're going to get. Yeah. Yeah. We will integrate sine cubed. In fact, I know I have one in here. I thought I had one in here. I don't. Sine cubed is a good one. If you see a sine cubed, do a u substitution. If you let u equal sine, no, let u equal cosine. I'm just going to do it off the side here. I'm going to do it quickly. So everybody put your thinking hats on. Sine cubed. If you face something like this, section 7.2 is this idea. But if you face something like this, you should realize that's a sine squared times a sine. Everybody nods their head and they say, yeah, absolutely, that's sine squared times sine. You say, great, let u equal sine. Actually, sorry, let u equal cosine. I keep doing that. And you say, why the heck would you let u equal cosine? Because you don't have a cosine that's gonna, that's gonna work. There's no cosine I see here. I say, I see one. Well, du is gonna steal away a negative sine. My pen is acting weird. Sine of x dx. Luckily, I do have a sine of x dx to steal away. So this is going to be the negative integral of sine squared of x du. And you say, see, I told you we don't have a cosine and we're still left with a sine squared. And I'll say, yep, but sine squared magically is 1 minus cosine squared. Pythagorean identity. And we know that cosine is u. Bam! Just like that. Negative integral 1 minus u squared du. So that is section 7.2, but just to give you a heads up, sine cubed does appear. And notice I had to use a Pythagorean identity there. So don't get too hung up on that example because it's not until 7.2, so I'm going to crawl away from it right now. And we're going to dive into this guy right here. So the first example in the tricky trig section was x times the sine of x. The second example was x times the sine squared of x. Now we're dealing with the power of x times sine of x. What do you do in that situation? Well, you're kind of in a bad spot. I'll say it that way. I'm going to teach you something that normally I would not teach. All right. So tactics. You could try a u substitution. It's not going to work because if you try to let u equal sine, it's going to need to steal away a cosine. And I don't see a cosine. I never will. If you let u equal, let's just pretend, 4x cubed, well, then its derivative, 12x squared, is going to be stolen away. But I don't have a 12x squared to steal away. And so again, no good. So my u sub idea is a bad idea. So I then think, well, what about by parts? Now, I've learned my lesson from previous examples. If there's any simplification of algebra or trig, I will choose to do it right now. But unfortunately, that's just a single little polynomial. There's no like natural log that I can pull apart like a taffy pull. And that's not like sine squared, which I can rewrite as 1 minus a cosine over 2 or something like that. Really, this is as simple as it gets when it comes to trig times polynomial. There's not much else that I could do here. So there's no algebra or trig before calculus I can do. So this tells me it's going to be strictly by parts, go. However, when we go to choose what to integrate and differentiate, remember, you want to choose the piece the largest piece to integrate. Well, of these two pieces, both of them could be integrated, or both are integratable, maybe I should say. So therefore, I then say, well, of those two pieces, which one would change forms if I start taking derivatives? And let me amend that statement. Which of those two will change forms if I take a lot of derivatives? Of those two, which will change forms if I am allowed? Yeah, if I'm allowed to take a lot of derivatives, the 4x cubed will change forms eventually. Not initially, but eventually. U sub 1 dv sub 1. The thing I'm going to take a derivative of is 4x cubed. The thing I'm going to integrate is sine of x dx. When I do so, d u sub 1 is 12x squared. V sub 1 is negative cosine of x. And we rejoice because now we know, yay, this is going to equal u sub 1 v sub 1, negative 4x cubed cosine of x. If you fell asleep at any point prior to this, this is where you want to wake up. Minus the integral of v du, or v sub 1 du sub 1. So minus the integral of a negative, so plus 12 x squared cosine of x dx. Now, I did mention earlier that what should happen when you do a by parts integration is that this integral at the back end loses complexity, that it doesn't gain complexity. It doesn't become an x to the fifth times cosine of x or something like that, but instead powers down a little bit. So we are on the right track. Yet, you could see we're going to have to do another by parts. And that's why I called that u sub 1. So let's do another by parts. Of these two, which can you integrate? Well, you can integrate either of them. So of those two, which one has a derivative that will eventually disappear? Yeah, you better believe it. The x squared. So the x squared derivative, again, notice I'm choosing, I don't change my position. In other words, if I chose to differentiate the polynomial to begin with, I will stick with that position for the rest of this problem. So here we go. We're going to choose u sub 2 to be x squared, and therefore dv sub 2 will be cosine of x dx. And thus du sub 2 is 2x dx. Oh, I didn't write the dx on this guy right here. There we go. And the v sub 2 is going to be sine of x, because that's the antiderivative of the cosine. And I say, yay! So let me go back up to that black ink up there. And for some reason, my eraser doesn't want to play along with me today. And let's go ahead and say this is equal to negative 4x cubed cosine of x plus 12 times the quantity. Let's see, u sub 2, v sub 2, so x squared sine of x,
minus the integral of v du, minus the integral of v sub 2 du sub 2. So that's going to be 2x sine of x dx. Well, I'll just move the 2 out. Wait, did I say 2? Yeah. 2x sine of x dx. I'll zoom out in a moment to show you that that is what we got. There we go. So that's just this product right here. And notice we still have an integral, but it's got less complexity. We went from, again, x cubed sine of x down to an x squared cos of x down to an x sine of x. Now we're almost done. So the final step here, we're going to integrate x sine of x, and you know that what's going to happen, right? U3 is going to be x, dv sub 3 is going to be the sine of x, dx. So that du sub 3 is dx, and v sub 3, the antiderivative of sine, is a negative cosine of x dx. And here we go. Let's go ahead and give ourselves some room here. Equals negative 4x cubed cosine of x plus 12x squared sine of x minus 24 times the integral. And the integral is going to be uv, u sub 3, v sub 3, so negative x cosine of x, minus the integral of v du, the integral of v du minus that business right there. So it's going to be minus a negative integral, so plus an integral of cosine of x. And then we have a dx, which I can barely fit in there. So the last integral that we have is actually a very quick integral. So the final answer is going to be a negative 4x cubed cosine of x plus 12x squared sine of x plus 24x cosine of x minus 24, and then the antiderivative of cosine of x is sine of x. And then don't forget, this is an indefinite integral, so plus c. Yes, those are common, by the way. Those are super, super common. So you can see by parts can be run many times. In fact, how many times do we run it? 1, 2, 3 times. And what was the power on this polynomial? 3. Does the dx go away from the v sub 3? No. The when we oh yes, it does. Yes, it does. It's sorry about that. When you do the antiderivative. Thank you very much. I'm thinking of something because I'm debating, do I want to teach you the trick now or do I not want to teach you the trick? Hard to say. Questions on this before I continue that inner dialogue of possibly doing the trick? Okay. If the question was, yeah, you have to do by parts. Yeah. If the question had an x to the 6 times, let's say, a sine of x, yes, you'd have to do by parts 6 times. So you could see right there, that's a good reason to teach a little trick that works in most situations, not all, but most. So here's the trick. I'm just going to do it anyway. We have u, we have dv, just like our little table. We had u and we had dv. What you can do if you know you have something that's going to go forever like this or go a lot like this, and usually that's polynomials and trig functions multiplied together, you could start this way. U is the thing I'm going to differentiate, which was 4x cubed, and dv is the thing I'm going to integrate, which was sine of x. Let's go ahead and talk about the derivatives of 4x cubed. Well, there are 12x squared, and then 24x, and then 24, and then 0. Those are the derivatives all the way down. The first, second, third, and fourth derivatives. I hope you all see that. Let's now work on that sign and integrate. The antiderivative of the sign is the negative cosine. The antiderivative of the negative cosine is the negative sine. The antiderivative of the negative sine is the positive cosine. And finally, the antiderivative of the cosine is a negative sine. I hope you all see that. Now what we're going to do is draw some lines. And I'm going to use red and green for this just to really highlight what I'm going to be doing. Okay. So, isn't it sine? Oh, yes, it is sine. Thank you. Oh, my brain. My brain today is like my brain every single day. All right. So let's go ahead and do this. I'm going to use green to connect these two. I'll use red to connect these two diagonals. I'll use green to connect these two diagonals. And I'll use red to connect the last two diagonals. Everywhere you see green means plus, and everywhere you see red means minus. Plus, minus, plus, minus. So if somebody said integrate 4x cubed sine of x, I could, just by drawing this, say the integral is equal to a positive 4x cubed times a negative cosine of x minus a 12x squared times a negative, so that becomes positive, sine of x, plus a 24x times a cosine of x, minus a 24 times the sine of x. Don't forget, you have a plus c at the end. What? That's right. You better believe it. That's good stuff right there. So it is very usable, very, very nice to use this this little table trick. It is essentially running by parts integration over and over again for you. So you're just setting up all the derivatives first and all the integrals first, and then you're running the plus and minus. Basically allows you, because you notice as we were doing the by parts integration here, it was uv minus v du, integral v du. So that's the alternating piece right there. That's where, so it's a positive uv minus the integral of v du. And then the integral of v du involved another uv minus integral v du in here, and the distributed becomes, that minus becomes a plus. So you get the plus, minus, plus, and the pattern continues forever. And it's just alternating plus minuses, and then you have derivatives attached to integrals the entire time. Very, very neat way of doing that very quickly. It's not really cheating. It's just a really cool trick. Really great way of using integration by parts. Now, you could tell, I can't zoom in because it's the top of my page, but you could tell up here, we're at page 10 of 18 because I really want you to be awesome with this material. It's still going to be due on Wednesday, but we'll just bleed this conversation over into Monday. But just to let you know, we only have really one. That's a really fun integral. 2, 3. I guess we do have a few left over. Yeah, that'll be Monday, basically. These are all really good integrals. And then we have a volume, and then a really cool question at the end. But yeah, so this will be our Monday. So it'll be a 3-lecture series on 7.1, or yeah, 7.1. In fact, let's just quickly, very quickly, we have 2 minutes left, tackle tan inverse. Can you integrate tan inverse? Do you know the antiderivative? Please say no. Okay, thank you. So if you don't know the integral, then that means you only can do either u substitution or by parts. And u substitution is just not going to work here, because what are you going to do? Let u equal tan inverse? No. So in this case, we're going to do by parts. U is equal to, and dv is equal to. Well, I know I can't integrate tan inverse. So dv is just dx. But I can differentiate tan inverse. The derivative of tan inverse, one of my favorite derivatives, one of the most important derivatives for this course, is 1 over 1 plus x squared dx. And then the antiderivative of dx is just x. So this integral becomes u times v, x times tan inverse, minus the integral of v, which is x, times du, which is 1 over 1 plus x squared dx. Now, could you integrate that? And if so, what method? No, you can't do it with the trig. It's a U sub on this one. This is going to be just a simple U sub. The trig means that you'd have to add one and subtract one, but unfortunately, adding one does not make it the same as the denominator. So the trick is not going to work there. But a U sub is very nice. If you let U equal, well, we've already used U. Let W equal 1 plus x squared, then dW steals away a 2x dx. I don't have a 2, but at least I have an x dx to steal away. And so that integral becomes x arctangent or tangent inverse minus 1/2 integral of 1 over w dw. It's supposed to be a w. I just didn't really pay attention. And now the integral of 1 over w, natural log absolute value. So as an example, this is actually pretty quick. Just peels off an extra page. Don't forget the plus C. And also remember, we did not start in the world of W's, so we can't end in the world of W's. Luckily, we know W is 1 plus x squared, and that will be our final answer. X tan inverse of x minus 1/2 natural log of 1 plus x squared. Notice I didn't write an absolute value because 1 plus x squared is never negative. It's not even 0. So you don't have to worry about the absolute values there. So some of the by parts, some of them can be fast. Some of them can be long. I'm choosing to teach the ones that are longer because the fast ones are just fast. All right. I've kept you long enough. I'm going to take a break. I'll be back in 9 minutes for office hours. Otherwise, you are free to go. You guys have a wonderful day if you're not going to be in office hours. But I will be there from 9 to 9:50. Remember, there is a quiz today. It starts at 10. And you can show up anytime between 10 and I will say 8:30 because it's a 25-minute quiz. So you want to give yourself time to do it. I had some people show up like 15 to 10 minutes before the quiz ended. They showed up at 8:45 p.m. It's like, well, sorry, you just gave yourself less time, but okay. So show up between 10 and 8:30 p.m. today for the quiz. All right. I'll be back in a bit. And on Friday, it's the whole lecture. You actually I give you 90 minutes for it, but yeah. All right. Be back in a few.